Welcome back to Summarize Science. When we search for life on other worlds, we typically look for planets in the Goldilocks Zone, the perfect distance from a star for liquid water. But it's not just about location. The star itself plays a huge, and sometimes destructive, role in a planet's evolution. Today, we're diving into a fascinating paper that models how a star's composition can determine whether its planets can even hold onto an atmosphere. The central question is this: does a star's chemical makeup, what astronomers call metallicity, affect its planet's habitability? First, a quick refresher. In astronomy, metals are simply any elements heavier than hydrogen and helium. Stars are constantly blasting their planets with high-energy radiation called XUV, which can literally boil a planet's atmosphere away into space. A star's activity is tied to how fast it spins, but all stars slow down as they age. This paper models that process and finds that stars rich in metals, shown by the yellow and orange lines, spin down much faster than metal-poor stars, shown in blue. This creates a puzzle. Metal-rich stars are individually more active, but they also slow their rotation faster, which should make them less active over time. So which effect wins out for a nearby planet? The answer lies in a surprising twist involving the habitable zone itself. It turns out that metal-rich stars are slightly dimmer and cooler than their metal-poor cousins of the same mass. As this chart shows, this means their habitable zone, where liquid water could exist, is much closer to the star. And being closer means getting a much more intense blast of that atmosphere stripping radiation. This is the crucial finding of the study, and this next graph shows the devastating result. These plots model the atmospheric loss of a planet in the habitable zone over 1 billion years. The different colored lines represent host stars with different metal contents. For planets orbiting metal-rich stars, shown in orange and yellow, the atmosphere is stripped away far more rapidly than for planets around metal-poor stars in blue and purple. For some planets with less initial atmosphere, this is the difference between keeping its air and becoming a barren rock. So, let's recap the incredible findings. A star's metal content is a huge factor in a planet's ability to remain habitable. Because their habitable zones are closer, metal-rich stars create a harsher environment that erodes atmospheres more quickly. This effect is most significant for stars similar in mass to our own sun. In fact, for these sun-like stars, their chemical makeup can be even more important than how fast they were spinning when they were born. This could be a game-changer for the search for extraterrestrial life. It suggests that the best place to look for a planet that has held onto its precious atmosphere might be around stars that are a little less rich in metals, giving astronomers a powerful new filter to help narrow down the search for another Earth.